The last topic in this section is the average value of a function over a region. So I've just got a picture up here to sort of illustrate what's going on. So if I've got some region R, I've shown here the signed volume that we would get if we were integrating over R some function f of xy dA. And just to keep the picture simpler, I drew it with a positive height function so that the signed volume is actually the geometric volume, but this applies equally well if the height is negative or if the height takes on mixed signs so that it's sometimes positive and sometimes negative. So this double integral is equal to the signed volume. And what I did here is I kept the base the same. So we've still got this same region R, but I pretended that the rest of this shape was made out of malleable clay. And I just morphed it a little bit, moved it around, took some of the stuff that was higher up, moved it to fill in the gaps lower down, and I evened it off to create a rectangular box that has the same volume as this. But for the rectangular box, the volume of that would just be the area of R times the height. And that's what we call the average value of the function. It's the height we would have if we leveled everything out so that we kept the signed volume the same, we kept the base the same, and we just made it so that all of the heights were constant. So if I actually go then and solve this for the average value, I can say the average value of a function is just the signed volume divided by the area of the base. Okay. So clearly the area of the base, we always count that as positive, so the average height will be positive if the signed volume is positive, and the average height will be negative if the signed volume is negative. This, of course, is just the double integral over R of my function divided by the area of R. So let's just do a quick example. Let's find f(av), the average value or the average height of f of xy equals x times y over R. Let's make that 0, 1 by 0, 2. Okay, fabulous. So I can say the average height is just going to be the signed volume, so that's the double integral over R of xy dA divided by the area of R. Now most of my work is going to go into doing the integral on top, so I'm going to calculate this first so that I don't forget. Now here, we're just working over this rectangle from 0 to 1 and then from 0 to 2. I can calculate that with just geometry. Base times height is 1 times 2 is 2. So we're going to take this double integral and divide it by 2. I'm just going to write that with a 1/2 in front. And then I can say we've got the integral from 0 to 1, from 0 to 2, xy. And let's see, 0 to 2, that was my y value, so we're integrating with respect to y first, and then x. Okay. So that's going to be 1/2 integral from 0 to 1 dx. That's just my shell. And inside of that, I'm evaluating this integral. If I integrate with respect to y, we're going to get xy squared over 2, evaluated between 2 and 0. And I'm plugging these numbers in for y. So 1/2 integral from 0 to 1. That's going to be 4x over 2 minus 0 dx. And of course, that's just 2x. So 1/2 the integral from 0 to 1 of 2x dx. That's going to be 1/2 x squared between 1 and 0. 1/2 minus 0. And so we just get 1/2. So that would be the average value or the average height of this function over that particular rectangle.